Okay, so self-information allows us to quantify the amount of information in a single event. To extend that to an entire probability distribution, we use Shannon entropy, which is denoted as Hx or Hp, like here. So we've got the equation, our Shannon entropy here is equal to the expected value of some random variable predicted by the probability of the information content in it, so the self-information. And we can rearrange that, we can reframe it based on the self-information formula that we have here. Based on that self-information formula, we can convert it into this other notation where instead of having information in there, we're just talking about the negative log of the probability of some event. So what this then allows us to do is it allows us to convey the expected informational content associated with an event drawn from whatever distribution we're looking at. So a low entropy distribution is roughly deterministic, and the outcomes are basically certain. As an example, if we have a weighted coin, a totally unfair coin that always lands heads up, then the probability of getting heads is equal to 1, and that's a low entropy distribution. A high entropy distribution, on the other hand, has highly uncertain outcomes. And so the uniform distribution, we talked about that earlier in our focus on probability distributions that are in machine learning. And so that uniform distribution can be the highest entropy distribution in a lot of cases. So for example, a fair coin that is as likely to be heads as tails, where the probability of getting heads is equal to the probability of getting tails, which is equal to 0.5, that is an example of a high entropy distribution. The probability of the two events is uniformly distributed. As a specific example of Shannon entropy that we can code up and play around with in this code demo, the Shannon entropy for a binary random variable, for example, a coin flip, right? So it's binary because there's only two possible outcomes, heads or tails. The equation for the Shannon entropy for a binary random variable is given by this formula here. So I'm not going to read it out. That sounds incredibly tedious. But I've encoded it here in this binary entropy function. So we pass in my probability, and then you can confirm for yourself in your own time that this math right here in Python is identical to what we have in the equation here. So let's play around with some values. So this function will throw not a number if we pass in a probability of 0 or a probability of 1, but we can get pretty close to those values. I mean, you can get extremely close. So as an example of getting very, very close to having always tails, we have 0.00001. Did I say enough zeros? I don't know, it doesn't matter. You get the idea. So the Shannon entropy, if we're basically always throwing tails, is extremely close to 0. That is a low entropy distribution. And we see the same thing if the probability is basically equal to 1. So if we get very, very, very close to 1, we get the same low binary entropy for that distribution. However, as we get closer to a uniform distribution, in this case a fair coin, so now that we are moving in that direction, so let's say there's a probability of getting heads 90% of the time with our coin, then the Shannon entropy goes up to 0.3, and the highest Shannon entropy that we can have in our binary distribution is where it's a 50-50 chance of getting heads or tails, and that's associated with an entropy of 0.7. If you don't believe me that this is true, that this is the highest Shannon entropy we can get with our binary event, then let's simulate some values. So let's get a whole bunch of probabilities ranging from very, very close to 0, so I'm putting 0.001, up to 0.999, so we're going to have 1,000 probabilities over that range in this vector p, and we'll pass all those 1,000 probabilities into our binary entropy method, and that will give us 1,000 Shannon entropies. And then we can plot the probabilities relative to the Shannon entropies expressed in nats, because we're using the natural logarithm in our formula here, right? So that's the NumPy natural logarithm. So our Shannon entropy is expressed in nats, and you can see that the peak of this curve is the point where the probability of getting heads or tails, say, is equal. That corresponds to this value that we had here of 0.693. So everything that we've been talking about in this video so far has involved probability mass functions, because we've been talking about discrete random variables. So a coin toss, that's a discrete event. We either have heads or tails. However, if we were working with a probability density function as opposed to a probability mass function, then the term to use instead of Shannon entropy is differential entropy. Nice, so Shannon entropy or differential entropy, these give us a way to calculate the entropy of a single distribution. So what if we want to compare two different distributions? Well, we're talking about that next.